Hi everyone, welcome back. Today we're going to start with phase diagrams, this time for partial solubility. We're going to do the same practice of phase fraction and also calculation of compositions for this kind of phase diagrams. I put the link into the description for the previous course. You kind of need that to be able to understand this one better, because that one we came up with easier example, and this is partial solubility, which is a bit more complex than complete solubility. So let's begin with this phase diagram. Obviously, as you can see here, we got a phase diagram of silver versus copper. On this side, you get atomic percent of copper added to silver, and up top you see weight percent of copper added to silver. So you can play with both, either with atomic percentage or with weight percentage. And you can work with this phase diagram. Again, we have our temperature. So first, let's pick something from previous courses, and then let's identify one interesting point here, and it is this point that we call this is our eutectic point, right? The minimum point in the phase diagram where your liquid is here, where liquid is going through a phase transformation and being transformed into solid, and two types of solid. So if this phase is alpha, and this is alpha, this is also alpha copper. So we have alpha silver plus alpha copper. Those are the two phases that we have available in this region. So that's a eutectic point, right? Going from, that was the definition of eutectic point. So you go from, for these two phases, which is solid 1 plus solid 2. If you have this minimum point that you have a liquid being transferred into one or more solids, just like that, then you get a eutectic point. So that is our main interesting point. Here is silver. Silver is 100%, so that's the melting temperature of silver. Here is copper 100%, therefore that's the melting temperature of copper. Those are the points that we can identify. This is a limited solid solubility. It means that you cannot add in any amount that you want to each other. You cannot dissolve them just like that. So you have limited amount of solubility while you have your silver matrix. So it's all 100% silver. And then you keep adding copper to your silver. This side of the phase diagram, it tells you how much at this temperature, at which temperature you can add copper to your silver and still get a single phase solution, just like sweet water. So this region is telling you how much copper at which temperature you can add to your silver and still get a single phase solid solution. And a single phase solid solution in here is called alpha Ag, or alpha silver. Alpha silver is a solid solution of silver and copper in single phase. The same on the other side of the phase diagram, when you are at the 100% copper, that side will also tell you, that would be this region, that would tell you, which is called alpha copper, is that it's a solid solution of silver and copper with some small amount of silver being added to it. And that tells you at which temperature, for what composition, you can still have single phase. And of course, whatever that is in between. And as I said last time, you do a horizontal line, and when you cross these phase lines, and then you know what's in it. So if you do a horizontal line from left to right, you're crossing alpha silver and alpha copper. Therefore, in between the phase, you have alpha silver and alpha copper. Okay. So therefore, this is our solid region, obviously, and this is our liquid region. And if we are here, we are doing a horizontal line again. So we are crossing the liquid side and also the alpha silver side. Therefore, here we have solid plus liquid, this region, because it's crossing these two. And also in here, we have, if, for example, you are in this point, you are crossing alpha copper region, and also you're crossing liquid region. So this is liquid plus alpha copper, which is just a solid, okay? And our solid here is also alpha silver. So these are the phase identifications and naming that we can come up with. So we know what we're dealing with. Therefore, in this, the line that has a border with the liquid is our liquidus line, and this is our liquidus line, right? And the line that has a border with the solid, with all solid, is our solidus line, and that will be our solidus line. This is our solidus line. And below the solidus line, everything should be solid, which is everything under the solidus line is indeed solid. So now that we have identified all this, now we can go with calculations of phase fraction for partial or limited solid solubility. All right. So for that, we just like the last time I said, for phase fraction and composition, you need to know two things. First, what kind of alloy that you have. Does it have 10%, 20%, or 40% copper or silver? And at what temperature we are talking about? Usually for practicing this kind of calculations, we pick a very high temperature and we start to cool down to see what kind of phases form and at which temperature what could form. And you need to beforehand identify the phases as I explained last time. So this time, by the way, if the speed of the video is too slow for you, you can speed it up. And is it too fast? If it's too fast for you, you can always slow it down, right? So I just go with my pace, but just know that you can change it. So let's go with phase identifications. How many phases that I show with P? How many phases or what kind of phases do we have? Well, we have one liquid. So our first is liquid. What is the second? We have here as alpha silver, and we have a third phase that is alpha copper, right? And in here, as I said, we have liquid plus alpha copper, which is mentioned here. The liquid is mentioned, alpha copper is also mentioned here, and we had liquid plus alpha silver. Liquid is mentioned, alpha silver is also mentioned. So that's all the phases that we have. Sometimes they can be 100% either of them, or they can be mixed of all of them. So first thing, we name the phases. We know what kind of phases we have. We have liquid, and in solid, we have alpha silver, and we have alpha copper. Fine. Now we need to know, pick the alloy. So we need to know what kind of alloy we are dealing with. These kind of information should be given to you, except for naming the phases, identifying the phases, like what kind of alloy, what kind of temperature should be given to you. You need to know that. So for this practice, let's begin with picking an alloy, let's say at 10%. And we start, as I said, at a high temperature, so we cool it down like that. So one alloy at 10%. Let's go for an alloy at 30%. We go for an alloy at 60%. And also for the last example, we pick an alloy with 90%. So it's going to be a long practice, right? We're going to practice almost all the situations to do phase fractions and compositions. All right, we have this. Now we're going to talk about the temperature. So we're going to pick a temperature. At first, we're going to pick 1100 degrees, and well, I'll do the first horizontal line, but you get the idea. So I don't do it. Probably it's not needed. We'll see to do more, but this is the horizontal temperature line that we do. But we have these whitish lines. We don't have to do that. So at 1100 Celsius, for an alloy that has 10% copper, we are at this point. For an alloy that has 30% copper at 1100 degrees, we are here. And for 60% copper, we are here. And for 90% copper, we are here. Okay. For the sake of ease, I call this alloy with 10% copper alloy number 1, with 30% alloy number 2, with 60%. I'm going by atomic percent, not by weight percent. And 90% of copper, we call it alloy number 4. Okay. Just like the last time. at 1100 degrees Celsius, what do we get? For alloy number 1, we are in the liquid region. So for alloy number 1, we get 100% liquid. For alloy number 2, we are here, we are in the liquid region. So also we get 100% liquid. For alloy number 3, liquid region, 100% liquid. Alloy number 4, also 100% liquid. Okay. So it's all 100%. Now we bring down the temperature. Now we go to 900 degrees. This is 900 degrees. Okay. Now let's see what happens for 900 degrees. 900 degrees, we are still at the line in here. So let's imagine slightly above the line. And then still we are here, slightly also above the line. And then for alloy number 4, we are here. So at 900 degrees, for alloy number 1, we are, let's say, still 100% liquid. For alloy number 2, we are still in liquid region, so 100% liquid. Alloy number 3, still in liquid region, 100% liquid. And alloy number 4, now for alloy number 4, we have entered the two-phase region, the region that we have liquid plus alpha. So for alloy number 4, you get liquid plus alpha. So we can begin our example from here. For all the other phases, we have 100% liquid, but for alloy number 4, which has 90% copper in it, we are now at 900 degrees in a region that has two phases, liquid plus alpha. So again, as I explained last time, when we want to begin with calculating phase fractions, you always start with a horizontal line that crosses the phase lines. What do I mean by that? Is that at this point, we want to do phase fraction. So what we do, we make a horizontal line that crosses the adjacent phase lines, just like that. That's what we do all the time. And if you watched the previous video, I did the exact same thing. So it crosses the solidus line at this point, and it crosses the liquidus line at this point, right? When you figured out these cross sections, when you did a horizontal line, you also drop it down. What I mean by dropping it down, from where it crossed the liquidus line, you make a vertical line now, get the compositions. So the horizontal line is mostly for phase fractions and the vertical is for compositions. That's what we need to do. Every time you want to do phase fraction and composition, you do a horizontal line, it crosses the borders. When it crosses the borders, you drop it down to go for composition. So for this point, we want to have phase fraction. Phase fraction of liquid is the amount of liquid to the total amount that you have. As I said, the total amount is the length of the line that is crossing the two lines. So the total amount is from this point to this point. If this point is 60, let's say 67 degrees, 67%, and this one, let's say just 90, also 97%. Therefore, your total amount is 90/70 minus 60/70. You still need to measure the amount of liquid. So you got 30 liquid over 30. So as I said, for liquid phase fraction, you need to cross the solidus line. The length of your line from where you start to the solidus line is your amount of liquid. That's how you calculate. So here, if it's 97, this is your solidus line, and the length of this line That's what we need to measure the liquid phase fraction. So this will remain 30, and then that is 97 minus 90, which is 7/30, right? That's your liquid phase fraction. For solid, we do the same. So it's solid for per total, and then it's solid to 30. The total amount will stay the same. And for solid, the length of the line that is crossing the liquidus line is the amount that we need to put in here. So if it's 67 and this is 90, then it's 90 minus 67/30, right? So this is it. So that would be 23/30. Yeah. So this is the phase fraction of solid, and this is the phase fraction of liquid. 7/30 is your liquid, and 23/30 is your solid. What it means that in your melting pot, when you started for alloy number 4, so we are talking about here. For alloy number 4, once we were at 1100 degrees, and for alloy number 4 at 1100 degrees, we had 100% liquid. Okay, so in your melting pot was 100% liquid for alloy number. But once you drop it down to 900 degrees for alloy number 4, which came to this point, it was liquid plus solid phase. So in your melting pot, some of it turned into solid at that temperature for this alloy. How much of it? 23 to 30 parts of it turn into solid. So majority of it at that temperature that you once had liquid turn into solid. That's your phase fractions. So at this temperature, you get these phase fractions. Now, I'll write them down here. So phase fraction of your liquid is 7/30. For solid is 23/30. And I get rid of these to show you about composition. So how we calculate the composition here. And finalize. I still need to learn how to kind of quickly erase a part of my screen. If you know how to do it, just let me know in the comments, because I still need to erase them. I don't know how to get a chunk and just delete them. Okay, now we have phase fractions. So for alloy number 4 at, this is how you can also write it. This is the way that engineers write for these kind of calculations, and that's understandable for many people. So for except for the handwriting, for alloy number 4 at 900 degrees Celsius, we had two phases, right? We had liquid plus alpha. 7/30 was liquid, and then 23/30 was alpha. What kind of alpha? Alpha copper. So that was our phase fraction. And of course, if you add them up, it will add to 3/30, which is the fraction of the total, which is 1. So that's correct. And we want to know about phase composition. So in your liquid, we want to know, again, we want to know if the amount of copper in your liquid and solid the same. Does the liquid have more copper in your melting pot that is part liquid, part solid? Do they have the same amount of copper or not? Some people make that mistake and say, yeah, they probably do, but they don't have the same amount of copper. How do we quantify that? That's how you do that. So again, from this point, which is the point of our interest, the temperature of our interest, if you want to know the composition of your liquid, you go along this horizontal line. When it crosses your liquidus line, and we also already dropped it down, so 67% copper is your composition of your liquid, where it hits your liquidus line. So in your liquid, you got 67% copper, where it hits the liquid. The same for your solid, the composition of your solid, you go horizontally where it hits the solidus line and you drop it down, and we already did, and it was 97%. Look how different they are. So let's start with the beginning of the story. For alloy number 4, which alloy number 4 has 90% copper in it. Okay, this is alloy number 4, where we started. This alloy number 4 at 1100 degrees was once all liquid. How much copper was in that liquid? 90%, because that was our original alloy. So at 1100 degrees, you had 100% liquid with 90% copper. When we cooled it down to 900 degrees, it turned into a two-phase mix, one part solid and liquid, with majority of it being solid. But the amount of copper did not remain the same. The amount of copper, as our calculation shows, was 97% in solid and 67% in liquid. So your solid part in that melting pot was almost pure copper, almost. And your liquid, which was surrounding it, it had much less copper in it. Imagine that you started with something. Imagine that you started with your alloy that has 90% copper, but if you cool it down, you can extract more pure version of your alloy with respect to copper. So you can get 97% copper. It's a way of purification, huh? If you start with 90% copper and you end up with 97% of your copper, which is here 97%, you are almost purifying your copper with respect to silver, right? So that's how you can read this, and it can change. Okay, this is about uh, 900 degrees. Let's pick the final temperature for our calculation. Then I promise you that's the final one, and then after that we close. Okay. So I get rid of these. Alloy is also gone, so we need this line for 90%. Okay, now let's move to, let's, let's cool it down furthermore. So we are, say, in this region. I think it's 800 degrees if I'm not mistaken. Yeah, now we are at 800 degrees. So at 800 degrees Celsius for alloy number 1, we are in pure alpha silver, 100%. We are in this region. It's just alpha silver is a solid solution of silver and copper in single phase. For alloy number 2, we are here, and we have therefore liquid plus alpha silver. For alloy number 3, we are here. So I'll put it here. For alloy number 3, we have also liquid plus alpha copper. And for alloy number 4, we are in this region, which means that we have liquid plus alpha copper, right? I think when we are done with this, then you should be really confident about knowing how to do phase fractions and calculations. So okay, so we have now this situation. So for 100%, we don't need to pay attention to that. Now let's go to point number 2. Point number 2 was here, and we want to do phase fraction for point number 2 at 800 degrees. So for point number 2, as I said, we always, for phase fractions, make a horizontal line and let it cross horizontally the phase lines on the left and on the right. And that's how we start with phase identification. Once you've crossed it, what do you do next? You drop it down all the time. Yep. This one, let's say it hits somewhere like here. And that will be our the beginning of our calculation. So for phase fraction of solid, uh, we first need to do the total amount. So if this is, let's say, 33, and if this is, for example, 13, then it's 33 minus 13. Okay, so that's your total amount, and the amount of solid is the horizontal line where it hits the liquidus line that we use for calculating the phase fraction. So the horizontal line, when it hits the liquidus line, it's 33 to 30. 33 minus 30. So it's 3 to 20 parts of solid. That's the phase fraction of solid for 0.2. And then phase fraction of liquid, therefore it's 17 to 20, obviously, because they need to become one. So that's the phase fraction of solid and liquid. It means that for alloy number two, at 800 degrees, you have 17 parts still in liquid. So the majority of it is still in liquid. What is the composition of this liquid? In your liquid, how much copper and how much silver do we have? You look at it where it crosses the horizontal line, where it crosses the liquidus line. So in your liquid, you got 33% copper. What about your solid, when it crosses the solidus line? In your solid, you got 13% copper. So your liquid in your melting pot, when they became two phases, the liquid part contains more copper, much more copper than your solid. Yeah. So this was about 0.2. Now, PowerPoint erase. Yeah. So this was for 0.2. Now we go for, I think also you got this, so I'll get rid of that. Now we go to 0.3. So for 0.3 at 800 degrees for alloy number 3, we are here. Again, we want to know the phase fractions. We do the horizontal line at this point until it crosses the phase lines on the left and on the right. And once it crosses that, then we drop it down all the time. We drop it down also here. And then that's what we need for phase fractions and compositions. So I get rid of the ruler. All right. So for this alloy that has 60% copper to start with at 800 degrees, the total amount, phase fraction, total amount is the length of the whole line that we have here. So if the line here is crossing, let's say it's 95, for example, and here is 45, then a phase fraction of your liquid will be the total amount, which is 95 minus 45. And the amount of liquid, it's where the horizontal line crosses the solidus line. So it's for solidus line is 95 to 90. Therefore is 5/50, right? And if you have 5/50 parts for liquid, because you have two phases and they have to add into one fraction, therefore, obviously the phase fraction of your solid will be 45 to 50, which tells you that for alloy number 3 at 800 degrees in your melting pot, most of it, 45 to 50 parts of it are solid, majority of it solid. So in your tiny, tiny amount of liquid, how much copper is in that tiny amount of liquid? You look at it where it hits the liquidus line. So you got 45% of copper in your tiny amount of liquid, and in your solid, which was the majority of your pot, is now turned into solid. How much copper you have, you look at it where it hits the solidus line. Therefore, it's got 95% of copper. So the whole chunk of your melting pot that has turned into copper, that has turned into solid, it has 95% copper. And the remaining amount of liquid which is just here and there is got 45% copper. So depending on how much copper you need, with kind of alloy with 45% copper or with 95% copper, then you know where to pick it. This part got 95 and this part got 45. So you can pick your alloy knowing how it is when you're working with phase diagrams, okay? So now also at point 4 looks awfully like point 3. Let's just do it for the sake of your practice, and I just do it so you can do it with me. I think now you can already start doing it with me to see if you got it right. Okay, for point 4, I'll just redo the temperature again. The eraser was not working, so I just took a bit of time to erase. But I do the temperature again on the ruler. Now we are talking about alloy number 4 at 800 degrees, phase fraction composition. What do we do again? Horizontal line, always horizontal line. So we do this horizontal line here until it crosses the left and right border. Then you have this line. Once it's hit it, what we do after the horizontal line, we drop it down. So we drop it down where it hits again. And then it comes down here for point or alloy number 4. And then you got this one. So this is the alloy that we are talking about. Again, 95 to 45. So our total is 95 minus 45, which is 50. Now for the phase fraction of solid, the total amount, the total amount is 50. Now the amount of solid, you cross it until you go horizontally until it hits the solidus line, the liquidus line. So for phase fraction of solid, this is the amount of solid that we have. So this is 90 minus 45. This is the amount of solid that we have, and phase fraction of your liquid is where it hits the solidus line. So it's 95 minus 90 to 50. So that's the amount. So this is 5 over 50. This is obviously 45 over 50. It tells you that for alloy number 4 at 800 degrees, you get 45 to 50 out of all parts in solid. What is the composition of solid in your big chunk that is solid? How much copper do we have in it? Well, we got 95% copper in our solid, where it hits the solidus line and where it hits the liquidus line. Here we got 45% copper in our liquid. So that's also the composition. That's all, guys. This is how you do phase fractions and compositions for phase diagrams for partial and complete solubility. I hope you learned something today. I see you next time. Bye.